So we were looking at Amdahl's law, and this looks at the execution time new in terms of execution time old and the overall speed up. So here is a simple problem. The problem states floating point instructions improved to run 2x, but only 10% of actual instructions are floating point. Right? So we're asking a question that we made an enhancement to the floating point instructions, and this improves the entire system by 2x, but only 10% of actual instructions are floating point instructions. The question is, what is the total new execution time and what is the speed up overall? Now, if you solve the problem by substituting, you would get this to be execution time old multiplied with 0.9 plus 0.1 by 2. That is 10% of instructions are floating point, right? And 90% are non-floating point instructions. So 1 minus fraction enhanced is 90%. Fraction enhanced is 10%. You're improving that by a factor of 2. So the speed up enhanced is 2. Right? So it's 0.95 into execution time old. So the overall speed up is 1 by 0.95, which is 1.053. Okay. Here is another example. This is example number 2, which says an enhancement that runs 10 times faster than the original machine, but only for 40% of the time. Right? So the question here says that you make an enhancement that runs 10 times faster than what was originally proposed, but now that occurs only for 40% of the time. Right? So you need to first figure out what is the fraction enhanced. 40%. 1 minus fraction enhanced, 60%. Fraction enhanced is by a factor of 10. So the solution is 0.4, fraction enhanced is 10, its speed up will be 1 divided by 1 minus fraction enhanced, which is 0.6, plus fraction enhanced, which is 0.4 divided by 10, so it's 1.65. And obviously, Amdahl's law is very much applicable for even parallel processors. Now, Amdahl's law, here's the summary for it. So if an enhancement is only suitable for a fraction of a task, we can't speed up the task by more than the reciprocal of 1 minus the fraction. So what this is trying to tell us is, let's say we have this fraction enhanced and we have the speed up enhanced, and we keep making the speed up enhanced more and more. That is, we are trying to diminish that term, which is fraction enhanced by speed up enhanced, and making it as small and small as possible. If it goes to 0, if it tends to 0, I mean that we completely speed it up, then we are limited. Our speed up is limited by the factor of 1 divided by 1 minus fraction enhanced. That means the serial portion of your code is the limiting factor for Amdahl's law. Now, one of the primary things to remember here is this is assuming fixed load problems, right? The problem size does not change with improvements. And this is where Amdahl's law limitation was understood. That is, if you are scaling the number of processes, you're not expecting the application also to scale, right? Now there is another law called Gustafson's law, which says how the speed up can be achieved by scaling the workload. So what we're trying to say there is, let's say you have one processor and you have this workload, right, which will probably take, say, 1 hour, right? This is the workload. Now, when you're going to have 5 processors, right, you expect that workload to diminish, right? This 1 hour to probably come to 45 minutes or so. That is under the assumption that the workload has not changed. But suppose that workload is increasing, right? With 5 processors, you increase the workload to twice of what it was originally for the one processor, or 5 times of what it was. Then you would see some amount of speed up, and that is a different law. Right? So keep in mind that this law is strictly applicable to fixed load problems. I will not study the other one in this course. So Amdahl's law is always applicable to fixed load problems. That is, the problem size does not change with improvements. So performance, what to measure, right? The next thing we'll see of measurements. Usually we rely on benchmarks versus real workloads, right? We look at a lot of benchmarks in the real world and study and evaluate them. Now, to increase predictability, we will collect benchmark applications of what is called as benchmark suites, and they're very popular, right? We use a lot of them for multimedia, for desktop, for transaction processing council. So spec CPU, this is a very popular desktop benchmark, right? This is a popular suite. We have CPU only, which splits between integer and floating point of programs. We have spec int 2000, which is specifically for integers. We have spec CPU 2006, which has both integer and floating point. Then if you want to look at server workloads, we have spec SFS, which is NFS file server, and we have spec web for a web server with server benchmarks and so on. TPC, which is Transaction Processing Council, generally measures server performance and cost performance for database systems. Right, so we have TPC-C, which is a complex query for online transaction processing. TPC-H, it models ad hoc decision support. TPC-W, it's a transactional web benchmark. And TPC-App is an application server and web services benchmark. So we have various benchmarks for web traffic, for server traffic, for looking at spec processors, desktop processors, and so on. Now you have all these benchmarks, and then you want to evaluate the performance, right? Now you get, you run different benchmarks, you get different numbers. How do you find out what is the effective value of that set of benchmarks on the processor that you're designing? One way we could do this is we can summarize performance by looking at arithmetic mean. Arithmetic mean is a very common way of looking at it. But they can vary 4x in speed. That is, some benchmarks could be pretty lengthy, right? And some benchmarks could be pretty small. That would create a discrepancy in your average mean, right? One benchmark would take 1 nanosecond to run. Another benchmark would take probably 10 nanoseconds to run, right? So you will see a discrepancy between the numbers, because it's not necessary that all those nanoseconds or all the latency units are going to cluster together. They might be quite disparate, right? They could be separated. So there's a problem if you take just arithmetic average. Another way is we could add weights to a program. We could say, okay, this, to balance it out, we could say this processor is weighted by this factor, or this processor is, this benchmark, is weighted with this particular factor. But then comes a question, how do you pick those weights? It's not an easy process to pick weights for different benchmarks. Someone might say, this is my benchmark, and you need to put a higher value to this, and so on. So different companies will want different weights for their products, because they are developing their desktop processors or their designs based on those benchmarks, right? So they may say we have to give more weightage to this and so on, which can be pretty tricky. So one way to normalize things is to use something called a spec ratio. So here you can normalize execution times to a reference computer, and what that will yield is a ratio proportional to performance. So what we could now say is time on the reference computer divided by the time on the computer being rated. So you have this computer, you want to rate this computer, you take the ratio with the reference computer. Okay, so if the program on the spec ratio on computer A is, say, 1.25 times bigger than computer B, then you can write this as 1.25 of spec ratio A by spec ratio B. Now when it comes to spec ratio, what you're saying is execution time of on the reference computer divided by execution time of A. The whole thing is divided by execution time of the reference computer divided by execution time of B. So you can cancel out the execution time of the reference computer. You are left with execution time of B to A, which is performance of A to B. So when you compare two computers as a ratio, the execution times on the reference computers drops out. So the choice of that becomes irrelevant, and you are now able to compare two different designs. So since ratios are very important, proper mean is what we consider as a geometric mean, right? Spec ratio is of course unitless, and arithmetic mean is meaningless. So the geometric mean is what makes a lot of sense, because the geometric mean of the ratios, right, that you're comparing to computers, is the same as the ratio of the geometric means, right? So it's not going to scale. It's not like arithmetic mean where there could be a variation of 4x or 2x between two values, right? You're taking the mean of the thing. So the geometric mean is the nth root of the product of the n different spec ratios, And all our results, if you look at today's research papers, we show our designs and we say this is the geometric mean of our design. Right? So the ratio of the geometric means is the geometric mean of the performance ratio. Choice of the reference computer is irrelevant. We don't look at it anymore. So it is just the mean of the geometric mean of different computers. Right? So that is one of the reasons why we always pick a geometric mean. So finally, what do computer architectures bring to the table? Right? So we bring in quantitative principles of design. So, for example, take advantage of parallelism, right? Use two processes, two cores, two pipelines, run things at the same time. So we take advantage of parallelism. The second thing is take principle of locality. We try to bring data elements closer to the processor so that we can act on them really fast. We focus on a common case, things that are very common in occurrence. We make use of them very often. We look at Amdahl's law, that is improving one aspect of a system does not improve the entire system. And the last one is a process performance equation, which is a basic equation that tells us how process performance is going to be. And that is in terms of instruction count times the cycles per instruction times the clock cycle. We provide careful and quantitative comparisons that we define, we quantity, and summarize the relative performance using spec ratio. We also want to define relative cost of the design, right? What is the cost of doing this? What is the real estate? What is the power that we require, right? And what performance we get. When we define large systems, we also want to talk about dependability or availability. How often is this system available? And obviously the last thing is power. So what do we computer architects bring is we bring a culture of anticipating, exploiting technology advances, right? How technology is going to advance into the future. We also bring interfaces that are very carefully implemented and that they are thoroughly checked. Right? So we bring interfaces between different systems. We try to say how technology is going to advance and how we're going to shrink things and so on. Okay, so this summarizes the performance metrics lecture, which looks into different aspects of computer design.